Okay, my name is Sergio Caldemarcano, and this is Computer Science course number 2 of the IB diploma. In this short video, we will try to demonstrate two short algorithms for checking if a binary tree is an implementation of a binary search tree. Afterwards, we will try to find more efficient solutions by outlining possible optimizations to our algorithms. First of all, we need to define what is a binary search tree. A binary search tree is a special kind of binary tree in which any key that it contains is bigger than those keys in its left subtrees and smaller than those in its right subtrees. So this is an example of a binary search tree. As you can see, each key in the binary search tree is smaller than its right parent, but bigger than its left parent. And this applies to each node in our search tree. Because of the definition of binary and binary search trees, these kind of data structures lend themselves for very expressive recursive algorithms. This means that when a solution is expressed in a recursive fashion, it can be easier to understand and more direct approach. So we have our first and intuitive algorithms that follows our definition. These algorithms would try to check if the key in the current node is smaller than that in its left child and is bigger than that in its left child and smaller than that in its right child. And we will try to apply this operation recursively for every node until one of its childs is null. Until the two childs are null. This means that until the node is a leaf. If any of these operations in the recursive function fails, then our tree is not a binary search tree. However, this algorithm may sound as a correct approach. We have to consider that it is not. So, for example, let's see the following example of a tree, in which we swap the 4 for an 8. Here, we can apply our algorithm definition and watch the point in which it will fail. So, we test for 7, which is bigger than 2 and smaller than 10, then we proceed to its left child. 2 has a left child of 1, which is correctly smaller, and a right child of 8, which is bigger than that. So the algorithm is actually working. However, according to our definition of a binary search tree, this node, being the child of a smaller node than the original root, is actually out of place and therefore violates the fundamental principle of binary search trees. How could we actually solve this problem? Well, the solution is rather easy. We only need to find the minimum and maximum value of the subtrees, and we can do that using two helper functions, which transfer the tree in order to find the leaves of the such tree. Following this algorithm will prove that this is not an actual binary search tree, but this is, which we swap the 8 for a 4, remember. However, these solutions would prove to be inefficient. Why? Well, because as our tree grows larger, we would need to transverse to the latest leaf, which means in the floor of our binary search tree, for each one of the nodes it contains. This is obviously very inefficient and wastes a lot of time. So this algorithm, although correct, is not ideal because of such inefficiency. How can we solve this problem? Well, there are two principal ways to solve this. The first one would be to store the minimum and max values of each node in the subtree as they are visited in order not to transfer a branch twice. However, this requires the use of an additional helper function, and so the implementation may not be as direct. Another, even more elegant solution, which does not waste the space required in the first optimization, is to transfer the binary search tree using an in-order transversal technique. And if any key in our transversal search is smaller than the previous item in the binary search tree, then the tree is not a BST. So we can solve this problem in linear time, which is big order of 10. Our last solution also follows big order of n, which is a linear solution but wastes some space. So thank you for your attention, and this is Ejibalde.